Hi, my name is Joseph and welcome to the Shoebox Mysteries. I'm calling it the Shoebox Mysteries because I use cool props, kind of like you might pull out of a shoebox, to explain the epic mysteries of the universe. For today are the conservation laws. Two of the most important conservation laws are conservation of energy and conservation of momentum. And we're going to use Christmas nuts and baskets to explain this. It's going to be awesome. Let's start with conservation of energy. Conservation of energy is pretty simple. It basically just means that however much energy is in the universe, that's what we get. You can't make energy, you can't make it go away. It's kind of like these nuts right here. We have a certain amount of nuts and they're all divided up between these baskets. By the rules of the universe, I can't take any other nuts that aren't already in these baskets and put them here, and I can't take them out and just say, oh, I'm done with that. But what I can do is I can switch forms. I can switch forms all day long. I can take nuclear energy and I can create kinetic energy. If I had a nuclear powered car, that's basically what I would be doing. Converting nuclear energy into the motion of the car, and then when I put on the brakes, then you end up with heat. So if I took this amount of energy and I converted it into kinetic energy, that amount of kinetic energy would eventually end up in this basket as well. Same thing if you're driving a gas-powered car, you would start with chemical energy, and then you'd end up with kinetic energy, and then that same amount that went into kinetic energy would eventually end up as heat. So this is pretty simple, pretty straightforward. Conservation of momentum is a little bit trickier. So let's get into that. Momentum is mass times velocity. It's basically a certain amount of stuff going at a certain speed in a certain direction. So right here I have my momentum off to the right, and right here my momentum off to the left. And the way this works is so conservation of momentum is not conservation of motion. So what conservation of momentum is it says that for every bit of stuff that's moving in that direction, there has to be a certain amount of stuff that's moving in the other direction in a similar fashion. So if I have if there are two ice skaters, say for example, here's me and here's you, and we're on the ice skating rink and we're skating around and we push off of each other, then we're both going to go in opposite directions. I'm not going to stay put while you go. You're not going to stay put while I go. We're both going to slide off in opposite directions if we push off of each other. Now, if I'm twice as heavy as you, then I'm going to go half as fast, and you're going to go I'm going to go half as fast as you. You're going to go twice as fast as me. So what we have here is we have twice as much mass. I'm twice as heavy, twice as much stuff, and so I'm only going to go back half as fast, and then you have, you're going to go. I think I made that confusing. So you see how it's pretty different. Conservation of energy is all about the same amount of energy always existing in the universe, and but only changing form. And then you have conservation of momentum, which is not conservation of motion at all. It has to do with the direction of motion and how much stuff is moving in which direction. In order to make something go in that direction, you have to make something go in that direction. If you want something to stop going in that direction, you have to stop it from going in this one. So I thought that was pretty interesting. That will help a lot for some of my future videos. I'm going to do some pretty cool episodes where we're talking about space, stuff that's in space, how stuff moves in space. We're going to come back to conservation of energy and conservation of momentum in a lot more detail. So stay tuned. Thanks for watching. If you enjoyed this video, please subscribe. I'm just getting started, but this is going to be a ton of fun.